In this session, I'm going to describe the power management features of the Oracle T5 system. The system I'm using has two SPARC T5 processors and 255 gigabytes of memory. Each processor has 16 cores, and each core has 8 hardware strands for a total of 256 CPUs on the system. The system is managed by Oracle VM Server for SPARC, also known as the Logical Domain Manager or LDOMS Manager. The system has two logical domains, both of which are running Solaris 11. This domain is the primary domain. This is where the Logical Domain Manager runs. The primary domain has 128 CPUs, all from one processor, and 127 gigabytes of memory. This domain, LDG1, has the remaining 128 CPUs and the remaining memory. Both systems are idle, and you can tell that with these graphs. Each bar here represents a CPU utilization. So when the bar is black, it means the CPU isn't utilized, and as the bar goes green, it means the CPU is utilized. So you can see that basically all 128 CPUs belonging to LDG1 are idle, and all 128 CPUs belonging to primary are idle. Now I'm going to describe the power management hardware features of the system. The power savings that we can achieve is primarily from the processor. The processor has two power savings mechanisms. The first is DVFS, or dynamic voltage and frequency scaling. Normally the processor runs at 3600 megahertz, but it can be stepped down to 800 megahertz. And software can set this frequency, DVFS level. This mechanism is also used by hardware to cap power, for example, when this chip is over current or over temperature. There's one other hardware power savings mechanism in the processor, and that's core cycle skip. 10 of the 16 cores in the processor can be cycle skipped down to 1/8. What that means is that instructions are only executed on one of every 8 clock cycles, bringing the effective frequency down to about 100 megahertz. We have one other power savings mechanism in the system, and that's coherency link scaling. Between these two processors, there are normally 4 coherency links carrying traffic, but this can be reduced down to 2 links, allowing the other 2 links to be powered off. Now I'm going to describe the power management software that controls the hardware power savings mechanisms. This window here is a web browser that's connected to the Integrated Lights Out Manager, or ILOM software, running on the service processor. You can see right now the system's consuming about 860 watts, and that's also shown in this graph right here. We can save power over that 860 watts by setting different power management policies. There are 3 policies in the system. Right now, we're running in the disabled policy. In the disabled policy, all of the resources are at full power, full performance. And you can see that with these graphs here. All of the cores at 3600 megahertz on both processors, and all 4 links are enabled. Performance policy is the default policy of the system. That's the policy that the system ships with. In this policy, components that are not assigned to a domain are put into the lowest possible power state. In addition, components that are assigned to a domain are allowed to be put into low power states as long as the latency to return back to a full performance is low enough to cause an insignificant performance impact. Our most aggressive policy is elastic. In this policy, we allow additional low power states that may have a longer latency, and when a load arrives, it may cause a performance impact until those resources are brought back to a full power state. Now I'm going to apply the performance policy. When you apply the performance policy on ILOM, it gets forwarded to the Logical Domain Manager, which forwards it on to each Solaris 11 OS. The Solaris determines what power savings features can be enabled in this policy. Starting with Solaris 11, we have a new power savings feature called Power Aware Dispatcher. The Power Aware Dispatcher is able to control the CPU power states of the CPUs that it owns. It can communicate with hypervisor and request that the cores in the processor get put into a lower power state. And you can see here that with this policy, the Power Aware Dispatcher has put 10 of the cores into their lowest cycle skip state, and the processor is also down to 800 megahertz. The tool PowerTop gives us visibility into what the power-aware dispatcher is doing. The power-aware dispatcher's algorithm is called race to idle. What this means is that when there is no work queued to CPUs on a core, the core can be put into the lowest possible power state. When work arrives on the CPU resources are put back to the fastest performance state to allow the work to get done as quickly as possible. As soon as it's done, the CPU resources are put back to the lowest possible power state. And you can see here that most of the time is being spent in the lowest power state on this basically idle system. Now I'm going to apply the elastic policy. Again, the elastic policy is forwarded to the logical domain manager. The logical domain manager forwards it to each OS. The power-aware dispatcher has already been enabled, and there are no other power savings features in the OS. And so there's no additional power savings from the OS. However, the logical domain manager also forwards this policy to hypervisor. Hypervisor manages the coherency links. And when it sees that the policy is elastic and there's not much traffic flowing across the coherency links, it disables two of the links, causing all the remaining traffic to flow on the remaining two links, and those disabled links are powered off, saving power. Now I'd like to point out the power savings we get from these policies. As I noted before, in disabled policy, we consume about 860 watts on this system when idle. When we apply the performance policy, this drops down to about 635 watts. And in the elastic policy, we save another 10 watts or so, which brings us down to about 625 watts total. So that's a savings of about 25% over disabled in the performance policy, and another percent or two, so 26 or 27% savings over disabled when in the elastic policy. We have one other new feature in Solaris 11, and this is the ability to set a Solaris-specific power management policy that can override the platform policy. So this tool, Power ADM Show, can control this. Right now, the policy that's being applied is the platform policy. And the policy that's sent over from ILUM is converted into a maximum latency that's allowed on the power savings features. This latency here allows the power-aware dispatcher to run. But let's say we wanted to disable all power management in the system. We can use Power ADM for that. We set administrative authority to none. This disables the power-aware dispatcher, and as you can see, all of the cores go back to full performance. In addition, the OS notifies the logical domain manager that any resources it's using should be put into the full performance state. The logical domain manager knows that the OS is sharing the coherency links, so it notifies hypervisor that it's no longer allowed to use low power states. And so the hypervisor puts the coherency links back to full power with all 4 links enabled. Okay, so now let me put the policy back to platform. But before I do that, let me just point out that while we're in this policy where we've disabled power management in this OS, it has no impact on the primary domain, and the primary domain's power-aware dispatcher continues to apply low power states to its CPU resources, as you see here. Okay, so now I'm going to start a load on this system. Note the power-aware dispatcher is once again enabled. When we start a load, you can see there's now a load on every CPU. The power-aware dispatcher sees the load has arrived and returns the cores back to a full power state. We have another new tool called LDM Power, which runs in the primary domain and communicates with the logical domain manager. This tool can show you the power consumption of the domains in the system. By default, it shows the processor power consumption. And you can see right now that LDG1 is consuming most of the processor power as it's running a load. And we can calculate this because we know the power consumed by each processor. We know which CPUs are assigned to each domain, the utilization level of each CPU, and the level of frequency that the cores and processors are running at. And using all this, we can come up with the per domain power consumption numbers. We can also see the approximate power consumption, memory power consumption of each domain. This is a little less accurate. Here we know how much memory is assigned to each domain. We know how much memory power the memory is consuming, and so we just apportion that power to each domain based on its allocation. We also can approximate the total power in the system that each domain is responsible for. And we do this by taking the ratio of the CPU power consumption that each domain is responsible for and applying that to all the remaining power in the system, the service processor, the fans, the I/O, and so forth, to come up with an approximation of how much each domain is consuming of the total power of the system. And here you see LDG1 is consuming about 75% of the power. And you can actually see the amount of power being consumed by the system overall with this command here. This 1094 is the same number you see up here. And then this also shows how that's split among the processors, memory, and fans. Now let me start a load on this system. And again, the power-aware dispatcher is running here. A load arrives, and the power-aware dispatcher notices that and brings all the cores back to their full performance state. Now I'd like to just quickly cover our fan control algorithm. We call this the intelligent fan control algorithm. When the system is sitting at idle and all of the components are cool, the fan control algorithm can put the fans at the lowest possible power, lowest possible speed, consuming very little power. Here we only consume about 14 or 15 watts of power when the fans are at their slowest speed. The fan control algorithm notices when work has arrived. It notices that the components are starting to get hot, and so it increases the fan speed. The fans can consume up to about 200, a little over 200 watts. So the fan control algorithm can save us about 185 watts when the system is cool, which is a significant amount of power savings for the system. I have one other feature I'd like to cover, and that's the ability to set a power cap. We have two power capping mechanisms, hard cap and soft cap. And I'll describe each of those. First, I'll describe the soft cap. So I'm going to set a target limit of 900 watts with a soft cap. And the way this works is ILAM monitors the power that's being consumed. And when it sees that the power exceeds the cap, it notifies the LDOM manager of the excess power being consumed. The LDOM manager calculates what's the maximum DVFS level that should be allowed to force the power down. And it notifies the hypervisor of this DVFS cap. And hypervisor enforces the cap in order to decrease the system power consumption. And you can see hypervisor has decreased the cap down to 800 megahertz, and here we've reduced the power down to 900 watts. The hard cap mechanism is different. With a soft cap, you can set any value between 421, which is the lowest amount of power the system will consume, up to 273, which is the theoretical maximum. It's basically impossible to consume 273 watts, but what this is a guarantee that the system will never use more than 273 watts. So ILAM and LDOMs worked together to try to achieve that 900 watts using the DVFS mechanism. It may not be able to, depending on what workload you've started, how hot the system is, and how low of a target you've set. Now with a hard cap, what you're actually setting is a guaranteed limit. So basically you're replacing this 2173 number with a maximum that the system will ever consume. Now the system can only achieve a guarantee down to a certain level. And if you try to set a target limit below that level, ILAM will know it can't actually achieve that level, and instead it will apply the lowest guaranteed limit. And so you can see on this page here that the limit that ILOM can guarantee is 1384 watts. It can't guarantee anything lower than that. So it's set that value here and notified you that it can't actually achieve what you've set. Now, the reason that ILOM can achieve this is because of an alternative mechanism we have, which is there's an FPGA in the system. ILOM notifies the FPGA of the maximum, in this case the 1384, and the FPGA directly monitors the power, and when it sees it's gone over the power, it uses a back door into each processor to lower the DVFS level, to throttle those processors down to a lower DVFS level. It can do this within milliseconds, and so because of the speed with which it can apply this throttling, this is why we can guarantee that this power is never exceeded by the power supply draw. And this means that you can actually lower the power that's provisioned to this system because you know that the power maximum is guaranteed. And of course, that saves power in the data center overall. So you can set a hard limit anywhere between the 1384 and the 2173 number you saw before. That's all I wanted to cover today. I hope you enjoyed the talk, and be sure to check out the Oracle Technical Network article on T5 and M5 power savings features. And thanks for listening.